Hopefully that has come through to everybody. Great, okay. Yeah, so unfortunately, yeah, but Melanie definitely was going to be sort of doing a duo with myself to actually do this presentation, but unfortunately she's not well today, so I'll go through this basically. So bit of background in terms of where we are at the moment. We're going to go through more about where we've got to with In2Track2. So I'll talk a bit more about what the history is of where In2Track2 comes from. But basically, the project finished in January this year. We've been working through on the next project, which started probably just nearly 15 months ago, which is In2Track3, inventively enough. And we're working through that at the moment. There was a bit of an overlap between the two projects, but effectively, it's the continuation, if you like, of what we've done in In2Track2 and In2Track prior to that. So just giving a bit of background in terms of what we have as Shift2Rail as a project. We have Shift2Rail as an overarching title for quite a suite of projects, and each of those are in what we call IPs, and IPs are innovation pillars. So all of these that you look at on this screen, these are all innovation pillars from different parts of infrastructure areas, such as stations, obviously management of traffic, etc. But the one we've been focusing on is IP3. So innovation pillar 3, looking at cost efficient and reliable infrastructure. So that's the area where we're sort of focusing our attention on in work that has been done from the In2Track projects forward to where we are currently. So the Shift2Rail project actually finishes in December next year as a complete suite of projects that's been running for quite a few years now. So it's a culmination of quite a lot of work from basically concepts, just thinking about how we can solve some solution, find some solutions to projects, the problem, sorry, that we've got within track infrastructure and switch and processing infrastructure effectively. So going right back to the start, the Shift2Rail projects that were track related went from the left-hand side across to where we are now. So Interrail was the first satellite project which started developing ideas and concepts about what we could actually achieve in terms of looking at issues that we need to try and find solutions for in basically in a infrastructure like track and S&C, that we have problems that we've been living with for ages, not just in the UK but across Europe obviously. And then it looked at these other projects as you're going forward through to In2Track itself, looking at track related issues as a starting point, taking further concepts from In2Rail forward, and then looking where we've got with the track related issues, In2Track2, which is what we're going to talk about a little bit more today. Some other areas where Interzone, which is currently what we call a satellite project that's running at the moment, and that's really looking at transitions between track and structures as a general topic of research that's been going on with that particular project. And then we are now with In2Track3, which is the project that's currently running. So this is really focusing on taking technology readiness levels from a very low TRL level and rail industry readiness levels that we have within Network Rail, and moving those progressively forward as the projects go from the one In2Track to In2Track2, and where we are with In2Track3 with track related issues. So moving further forward, where we are and what we're actually trying to achieve in terms of the outputs of In2Track2 and then In2Track3 related to what we mentioned earlier, is to build some technology demonstrators of what we actually have done with solutions that we found for both issues that we know of within track we currently have, but also looking at, well, okay, if we start with a clean sheet of paper, what will we do differently? How could that be done? Some method of actually achieving the objective of reducing the actual delays we might have and defects we might have with current technology, to what that might look like if we're starting with a clean sheet of paper, and what actually could we develop to actually achieve the objectives. So in terms of what we're looking at here is switches and crossings and plain-land track. So as you can see there, you've got two work packages, which is the WP1, WP2, WP3, WP4 in both of those different areas. So work package 1 is looking at enhanced S&C demonstrators. And what that means really is we currently have S&C in track now. We know lots of failure modes that we have to struggle with in both, obviously the work package 1, which is for S switches and crossings, and work package 3 in the plain-line track. They're looking at what have we got now in terms of infrastructure switch and crossing types, plain line track, and what failure modes have we got that we really are fighting to try and actually resolve. So let's have a look at those a bit closer and find some solutions to those as far as we possibly can do. So clearly the projects before In2Track2 started identifying what these issues were. And obviously we know within Network Rail what a lot of our problems are, but clearly this is a European project. So it's really trying to reflect what the problems were in Europe, which are not different totally from ours. Obviously their infrastructure is slightly different in some cases. So it's looking at how we can actually relate to those and work on solutions for some failure modes we currently have struggles to try and actually achieve performance and reduce the number of defects we can have. The work package 2 and work package 4, as the name suggests, it's looking at next generation for switching and crossings out of plain line track. So effectively, what could we do differently? How can we change things to actually improve performance, reliability, and reduce the amount of defects we get? And obviously taking into account the actual knowledge we've got from current asset types, etc. And then there's also work package 5, which I'm not going to go into a great deal because obviously it's talking about tunnels and bridges, which is clearly out of my expertise. So there is a lot of work obviously gone on with that particular work package as well to actually look at how they can maintain and maybe design the actual assets in their particular area a bit differently to what currently is used. So in terms of In2Track2, for the plain line aspects of it, we've looked at autonomous inspection and repair, track and S&C maintenance, obviously S&C is in there as well. So looking at monitoring and sensing systems. So these are just headline subjects that we've obviously got within the work that's being carried out. So kinematic systems, we're talking about point operating systems really. So actuation, locking and detection, and what we have issues at the moment with current systems we use and what we could actually change to actually improve that. Design materials and components, so that's across the board for switches and crossings and for plain line. Autonomous inspection is part of switches and crossings as well, which we'll go into a little bit more detail later. Monitoring systems obviously is something we're quite keen on to try and actually introduce it because we haven't really, well, we're scratching the surface in terms of what we use currently. And the other part is digitization. So looking at how we can investigate how we need to actually build a track and switch and crossing digital twin. I won't go into details about what digital twin means and what it doesn't mean, but basically that's some work that's looked at trying to make in high level, a digital representation of the track and S&C, but to actually look at that as in the longer term, to use that as a maintenance tool, which means we can look at how things degrade component-wise from real-time information that comes from monitoring systems to feed into the digital twin to then gives us some asset life prediction and how we can improve that by changing certain components, etc. So digital twin is quite a key area where we need to actually do a lot more work than we've done so far, and it's quite a very technologically advanced area of work that needs to continue. So in plain line track, these are the projects we're going to talk about a little bit. So autonomous inspection and repair. So in these particular piece of work with In2Track2, we looked at autonomous ultrasonic rail inspection, developing something that's more automated. Automated rail defect repair, that's the DDR, which is a discrete defect repair machine, which again we'll go into a little bit more detail. Rail stressing, how can we do that differently maybe compared to how we do it now and what tools we use, what equipment's available. And monitoring and sensing systems, so looking at thermal rail stress measurement and particularly track stiffness monitoring. So they're the projects we'll talk about a little bit further as we go through. But looking at autonomous inspection, there's lots of areas where we can actually take forward the ideas from various different aspects of what we mean by autonomous inspection and repair, and clearly looking at how we actually take the data. We're very good at creating data, but really using it, making it more user-friendly so it's not too complicated for people to understand and how they actually need to operate it is a key area where we need to interface with lots of different systems, but clearly make it something that's quite easy for us to actually get the best out of it. So moving on to the autonomous ultrasonic rail inspection, this is sort of linked to another project you may have seen on that list earlier on, where it's talking about InterSmart and InterSmart2. And InterSmart and InterSmart2 are more looking at control systems. So obviously, if you're going to have an autonomous vehicle, you need to have a control system to make sure it actually works the way you need it to. And this is basically a platform called the Warthog, which was bought for this particular project, which is an autonomous vehicle effectively. It clearly isn't designed to go on track. It's just a system that's a platform that's been used to actually show how it could use this sort of technology and convert it to a rail version of this similar equipment where it can actually go to a certain location, do a test of an ultrasonic nature in this case, obviously check to see if there are any defects, and then obviously then identify where those defects are. And clearly the next system, which would be the Eureka moment, would be having some repair system that actually comes along after the ultrasonic system's detected a defect, and it actually takes the defect out autonomously as well. So this is where this is going to link in terms of work within the In2Track2 project from the track aspect of it. But obviously, we need to liaise with other projects to actually understand how we actually control these type of vehicles. And this type of thing is on the agenda and will be something we're looking to drive forward to automate as much as possible where we can to actually remove the human factor issues, which can be a problem in some cases. So the discrete defect repair machine, this has been work that's been looked at in other projects outside of the In2Track suite of projects. But effectively, it's an automated system to actually repair defects in plain rail. It's a solution that's obviously looking at how we can take spots out, wheel burns, those type of defects that we see quite commonly in the plain rail, but obviously taking out the actual person involvement other than operating the machine from a tablet system. And it's fully automated, and it actually does everything that you need to actually take out the defect, fill the actual void that it creates with weld material, and then reprofile it to actually finish off the rail back to a as it was found situation. So not as new, it will really take into account things like side wear on either side of the actual defect itself, and making sure it blends into that area. So it's got an automated clamper system. It's got a laser profile measuring system, which obviously it needs to make sure it knows what the profile should be that it creates after it's completely finished the actual weld. Basically, where we are at the moment, this is sort of linking to some work that's basically In2Track3 a little bit, but this is what happened where we got to within the work that finished off in January from In2Track2. So that's the machine there effectively without any guarding on it, and that's in the actual area where it's been tested to actually show it could work. A few things that need resolving in terms of things like guarding and be able to get this on track to allow it to actually operate. And we're going to be doing a trial of that in the next couple of months to get that actually worked through. So effectively, it's milling out the defects, so it's not grinding or anything like that. So it's obviously something, as you say on here, quite a lot of industry first. It's got a low temperature weld restoration, so it doesn't use really high heat compared to what we currently do with technology that we use currently for defect repair. It's got an air cool system, obviously requires that to actually keep the temperature down a little bit rather than actually having it turn too high. And it's all CNC operated, so it's all controlled by a computer numerical control system for the milling head, which is obviously again something that's not been used before. We've also then
I only succeeded in losing the picture completely.
So you can't see anything.
No, it's the bit at the bottom that was annoying me, but I couldn't lose it. No, it's this,
Okay.
I know.
You okay?
Sorry, Phil, I don't know if you could hear me. I couldn't hear her. All I could tell she was speaking, but I couldn't actually hear.
Yeah, not to worry. We'll carry on. Okay, this has been demonstrated on grade 260 rail, but we're looking obviously at other rail types that we have in our infrastructure for developing things for HP in particular, because of the rail that we've used in the last few years. We'll look at finite element modelling of the thermal history of the actual metallurgy between the actual weld material and the parent metal. So making sure obviously we don't actually include any inclusions or defects that might actually affect the quality of the actual repair. So where we've got to at the moment in terms of what the system is needing now is obviously approval for a guarding system to go over the actual operating system itself, so the machinery, to then look at how we actually do that from a safety perspective. That's obviously something that we've just about got approval for now, but obviously it's going to then look at how that takes the logistics of getting the machine onto track into a different level. And that's going to probably be done by something like an SRS machine, which is something that can be a truck with a bed on the back of it that can actually demount the machine into the right area where it needs to go. And then obviously it can be operated and then taken off track by the same method. But here's a couple of videos that show how the actual machine works. There's a few that are 20 seconds long maybe, that just show a little bit more detail about what actually is the machine and how it works. And this milling head's taken forward through the actual removal of a defect by milling out the pocket to actually get that opened up to the right depth of what we want. So obviously we're talking about widths of railhead between 50 to 100 millimeters long in terms of defects we can take out, looking at the time it takes. But obviously that can be extended if you've got multiple defects like a wheel burn. You can actually take 2 of those segments out next to each other if necessary. But obviously the time for the process to finish is going to be a little bit longer to actually allow that defect to be repaired properly. So this is obviously the next stage of welding the actual cavity to bring it back up to a profile that's above the rail that you've got in either side of the actual repair. And that's basically what it looks like. Nothing fantastic in terms of actually what it achieves. In the way it does it is really a key thing, because obviously it's a key thing for anybody who's into welding, knows that the distance between the actual wire and the actual weld itself is going to be a key area where it needs to maintain that distance. So clearly the machine needs to know that and obviously adjust itself as it needs to make sure it actually keeps that distance consistent. Again, using PLC itself, programmable logic controller, it actually allows the system to be very well controlled. And at the moment, as it says there, we do it in multiples of 3 millimeter layers, depending on the depth that's required. This is how we've got to take the actual slag, if you like, off the top of the weld itself. And these fingers, so to speak, excite and obviously remove that material. So what you see when you finish the weld, you've got the actual center photograph in the middle there. You've got that slag on the top of the actual deposit, and then on the right hand side, what you need to clean it to actually allow that slag to be removed to therefore then allow us to mill it. And that's done between each weld bead layer to make sure obviously it exposes the bare weld material to allow the next layer to be added to it. And then obviously once you put the deposit down, you need to actually reprofile this to actually get back to the rail profile you have either side of the defect. And this is just showing how it's done. And this is obviously on the right hand side is the finished surface finish of what you see. The left hand side is looking at it, taking a profile with the single point laser that actually goes over the rail, and then obviously it shows what profile. Well, you can compare what the profile was measured before it was actually repaired, either side of the repair, and then obviously what the profile of the repair itself is, and make sure it marries up so there's no lump left in the rail itself that allows a defect, if you like, to be a problem for the train wheels coming back over it. So that's basically how that's actually moved forward. So quite a lot of work's gone into that development over the last 2 years to get this to the stage where it's at now. And we're just about at the stage now where we can actually take it on track, do a little bit more validation work after we've got the guarding put in place. So theoretically, we're looking at other areas of delivery, and that might be on the mobile maintenance trains, as well as using something like an SRS truck with a rail vehicle to actually take it on track and move it to whatever site it needs to go to. But it's going to be a system where I think with the actual work they've done so far, a repair takes about an hour. But obviously it's clearly all computer controlled. It's all take away the actual welder, the interface of the human factors and all those sort of issues. So you get consistency, and it is very reliant in terms of its actual use. So moving swiftly on to the next part of the plane line work. This isn't really something that's new in terms of what people have seen in terms of this. We may have come across the actual flashbook welding head that's been developed by Mirage. There is some work that's actually been looking to try and see if we can actually do the stressing at the same time as doing the weld. So quite a lot of work's been gone into that to try and understand a little bit more about how that could be done. I don't think it's got quite as far as we were hoping at this stage, but it's obviously a possibility for this to actually allow that stressing to be carried out at the same time as welding a rail in future with this this system. So I think it's a case of just understanding a little bit more about what needs to be done to work with this company to get this actually available as part of the service that this can provide in terms of welding rail together. Rail stress management. Obviously, we use various different systems at the moment to look at how we actually measure what stress we have in a rail. But this is looking at some method of ultrasonics to actually understand what we actually could use for new technology to actually look at how we can actually manage and measure stress better than we currently do with things like burst testing. So again, this is work that's in development from In2Track2, getting to a sort of TRL stage of sort of 3 and 4 at the moment. So it's a little bit way to go before it's something available for us to actually start using in track, but it's looking very promising. Other parts within the In2Track2 project is looking at stiffness monitoring of track. Clearly, it's an area where we've got quite a lot of areas of data that we can actually see from things like the MMT, etc., and looking at how that works. But clearly, there's two sides to this: is looking at, well, what's the stiffness from the track point of view, and what does the vehicle see? So clearly, if you've got some accelerometers fitted to a vehicle like the NMT, you'll get some data obviously seeing it from the vehicle perspective, which clearly could be quite different from what the track perspective sees. And looking at these and looking at the data that's been captured from these particular systems and putting them into a model to understand what each of them is saying and translating the information to see what the track and the power car sort of relationship actually looks like is a key area where this track stiffness monitoring is going to hopefully give some good results to actually allow us to show how that track stiffness could change over time and obviously what that effect has on the track. So that's a quick run through the actual plane line track elements, which is mainly from Melanie's work, which is she would have done that presentation if she was well enough, but unfortunately not. And moving up to my area, which is switching crossings work, we've again looked at autonomous inspection and repair. So similar to what we've done with the discrete defect repair machine, we're now all going to look at doing a crossing restoration machine. It's a similar sort of machine, but looking at obviously how we can repair a defect in a crossing and a wing rail. So we'll go into that a little bit further in a minute. Early inspection of S&C, there's some developments in that. We're looking to try and actually move that further forward in the In2Track2 project as well. But I'll give you a run through of what we've got so far with that. Looking at track and S&C maintenance itself, additive manufacture or 3D printing, if you want to call it something slightly different for S&C components. We've been looking at how that might work and what we could actually achieve from having that as an option to use for creating components in future, and what advantages and what disadvantages there are for those particular requirements for different components that we might actually need this expertise and this technology. Handheld scanner, this is really looking at how we can do a quick scan of a switch rail and understand whether we've got an 053 switch derailment hazard that we need to do something to actually protect traffic from actually having that switch to run over due to the issues that we've got. So this is moving away from maybe using a handheld gauge, the track gauge we've got with P8 profiles on it, which are used commonly everywhere at the moment. There is some other work going on with a slightly different scanning system, but this is the basis of what we're looking at to try and actually have some instrument that's quite quick and easy to use and translate. NR56V crossing profile optimization, bit of a mouthful, but basically we introduced a new switch and crossing design called NR60 Mark II probably back in 2017 when the first installation occurred at Thirsk. But as part of that work, we optimized the crossing profile of the NR60 Mark II crossing itself to reduce the actual impact loading that wheels actually put on the crossing as they traverse from the wing rails to the crossing nose. So what effectively we're doing with this is doing similar work, but for the NR56V crossing itself, which is quite different in terms of the technology because it's really £113 that's brought forward to be dubbed an R56V. But the profile itself is quite different in terms of how we need to actually optimize that and how the wheels actually behave as they go over the crossing. So we'll talk about that a little bit. And then coating of switches. So this is looking at seeing if we can actually add a coating to a switch rail, or maybe a cladding, perhaps, if it's going to be a bit thicker, to actually reduce the actual wear rates and friction on the actual switch rail itself, to actually increase the life of the switch rails. And it's obviously assessing whether that actually is something that would be a benefit or perhaps not, depending on obviously what the results are. Monitor and sensing systems, just focusing on one particular aspect of work that's actually in In2Track2, looking at the location of S&C through using RFID technology. I'll explain a little bit more about that as we get towards the slide. And then Kinematic Systems, it's really looking at a complete different type of switch and crossing, or way of moving traffic, if you like, from one rail or from one track to another, using a system which you may have heard of in the past called Repoint, which was developed by Loughborough University some years ago, but didn't necessarily get very far in its actual development to actually get to the stage where it could be used as a potential system that we can put in track. So those are the ones that we'll go through in a second. So autonomous inspection. Drones themselves, obviously there's lots of drones being used by various different industries. We're using them for things in network rail, for things like embankment, OLE, structures. Track is a little bit of areas where we're sort of dabbling in terms of trying to do some inspections with a drone. The main problem for us for actually using a drone in terms of plane line inspections, for example, is the Civil Aviation Authority requirements mean that we can't have a drone flying out of line of sight. In other words, the operator's got to still be able to see where the drone is. So clearly, if we want to do inspection of a 5 mile stretch of track, as perhaps we do at the moment, basic visual inspection of somebody walking the track, obviously the actual use of drones would be great, but clearly you can't see it from one position, where 5 miles down the line the inspection's carrying out through using a drone. We can't actually do that at the moment. So there's some areas with the actual requirements from the Civil Aviation Authority that need to be worked through. And it's not just you network rail and railway infrastructures that have got this problem. People like power systems in terms of the national grid, etc. Those type of industries are looking for the same sort of flexibility. So obviously there's work to do yet to get that agreed in terms of the actual red tape, if you like, for actually flying a drone in that respect. But effectively, going back to where we were with this, so we looked at doing some trials in February last year. We started looking at what we could actually achieve with a drone. So effectively, this drone itself can take footage at, I think we actually developed it to do 20 meters height at the moment. We're looking at taking it to 35 meters. Effectively, that's the sort of footage you'd see. So the left-hand side is basically something that's seen from the height of what the drone was flying at. The right-hand side is exactly the same footage, but zooming in on that. But to allow us to actually get to that clarity, we need to actually look at what we call a ground sampling distance. And that's the distance between, if you think about your television, you've got different pixels on your TV screen to actually show you the full picture of what you're obviously watching. The distance between the center of one pixel to the center of the other pixel next to it is this ground sampling distance. So we had to get that down to about 0.94 millimeters, what we achieved, which is quite a challenge to make sure we got the actual clarity of the footage that we wanted to show how we could inspect things, and obviously get the detail that we'd expect somebody to see when they were walking the track. So that was a challenge in itself. So there's more work to actually look at how we can take dimensions off that footage. But clearly the other part of that is looking at, well, how can we actually look at what changes might have occurred since the last inspection. So looking at things like plane light pattern recognition from a train point of view, can we do that with a drone? So effectively, yes, you can. And this is obviously a few slides here that will show what's actually been developed so far to just basically show the concept is feasible. You've got to train, obviously, the model to see what it's actually looking at is the footage of what the drone is showing. So this is still footage, it's not a video. You can actually mark up the clips in this case just to understand exactly what the software needs to see. So you've got to teach the model effectively what does that clip look like and what position are you saying looks okay? And when you look at some other clips, what position you expected that clip to be in? And obviously, if it's not in that position, how you actually flag up that there's something different occurred. So effectively, you run the imagery and put that actually that requirement for where clips are to be actually identified, and this is the type of thing you get within a few seconds after it's been trained to recognize that. We've moved that on further, so if you start on the left-hand side at the top, you've got all three. You've got the clips, the screws for the base plates, and the bearers. But each of those other sectors in the squares there are obviously just areas where those particular components need to be trained in the software to be recognized by the software to say where it is and is it actually present or not. So it's machine learning effectively to understand exactly what the footage you're seeing and where clearly what particular components you're interested in and where they are. So what I'm going to do with this is a picture of two surveys. So this is a still photo. I'm going to click on the link in a moment. So one in March 2021 and one in September. And the cursor in the middle is basically separating those two surveys. So if you move the cursor left and right, you'll see what's different in terms of the actual inspections. Hopefully this will work. So this is part of the software that's been tested, if you like, to actually show what we've got here. So this is obviously a very high level view of the track. So I'm just going to zoom in to the piece of track to actually show where things have changed. Just move it along a little bit. Zoom in quite a bit. So all those triangles are obviously areas where the software is recognized as something not quite the same as it was before. So if I zoom a little bit closer, you can see on this one in particular, it's obviously got this identification mark over the clip. So on the 5th of May last year, the clip was in that position. And obviously the other inspection in September on this side is slightly different. So if I move the cursor over, you'll see what happens when the clip is passed over. The clip's moved, it's obviously come out over that time. And that's what this type of software can do, and that's the sort of powerful sort of imagery you can get that clearly is quite easy for anyone to use to actually show any difference that might have occurred between two inspections. So on the left-hand side here, you've just got a count, if you like, of different bolts and clips. And the ones, obviously, the discrepancies are these hazard triangles here, these yellow triangles with an exclamation mark, indicating that something seems to have changed, and you need to have a look at that to actually understand what that is. And obviously, in this case, the clips come out. So it just shows that type of thing where we actually can use the software to actually articulate what has actually happened in terms of inspection purposes, and clearly it can be identified and pinpointed to where we need to look rather than actually having to look through the whole of the actual SNC unit and inspect it individually just by somebody looking at a video. So that's the technology basically of where we are with the drone itself. So that's a work in progress in terms of where we are with that work. We're looking to take this further forward to actually develop this to a point where we can actually start showing it as a potential for us to actually introduce something like this in future. Okay, autonomous inspection. Moving forward to autonomous repair, we're looking at, as I mentioned before, how we can actually develop something that actually will repair a crossing automatedly. So it actually doesn't allow us to have the problems we've got with weld repair crossings at the moment. So those that maybe not familiar with crossings too much, you've got a different profile on the crossings, and obviously it depends on the angle of the crossing, which is an issue in one sense that needs to be considered. The direction of traffic can be another problem where you've got one particular part of the crossing, one side actually seeing more wear than the other. So that needs to be something that's looked at to understand how we actually repair a crossing to make it suitable for traffic still to run that direction, but clearly taking into account the less worn side that's on the other side of the actual wear the area we need to repair. But obviously the thing that is important for us to make sure we sort of look at the wing rail and crossing nose relationship. So at the moment, the bigger problem for us is actually the height difference between the nose of the crossing and the wing rail. If we start getting batter on the wing rail itself or the crossing nose more commonly, that height difference can increase. and it's just then a vicious circle. You get more impact through acceleration of the wheels hitting the crossing nose as they pass over that gap. Therefore, you get more batter and more damage occurring on the actual crossing itself. So theoretically, if we can actually repair the wing rail and the crossing nose, so we can reduce that gap, even if we're recreating a sort of a worn profile that maybe is required because of the actual wear that's been seen on the crossing itself, we can reduce the height difference between the nose and the wing rail. We can reduce the actual impact loading that the wheels are putting on the crossing. Therefore, bring us back from the actual point of where we might actually then develop a crack in the crossing or break the crossing itself. So we can actually manage our crossings a lot better. We can actually reduce the damage that we see, and we can obviously increase the life of the crossing itself ultimately. So, like I said, a DDR machine, we went through quite detailed review of what that does at the moment. This is work that's ongoing at the moment. It's actually got to the stage where we're developing the crossing itself, crossing machine, sorry. But obviously, if you can have a look on the right-hand picture, this is a plain piece of rail. This is just something that was done earlier this year to actually show that the software could create a crossing nose profile and how it actually would actually mill that out of something solid like this at the moment. So that was just a development phase to try and understand what was possible with the software, how it actually worked, and how we created a profile of the nose itself, because obviously the actual gradient of a crossing nose as it comes up from the point is quite different in terms of different crossing angles. So it's a key area for that actual to work through to actually understand what software needs programming to actually give us that profile that's required, and obviously taking into account any wear on the wing rail and crossing that need to be factored into the repair itself. So moving to additive manufacturing of components. Well, this is something that we've looked at because of issues maybe in terms of legacy components. If it's a specific component that's bespoke to a junction, it might be a case of actually, if we try and actually order a new one, we might be able to get that order put through, then the manufacturer might have actually not made one for 20, 30 years. So the mold, because we cast obviously most of these at the moment, may have been ditched because they deemed it never being used, so why are we keeping hold of it? So what we can do in some instances is look at reverse engineering componentry. So what you see on the right-hand side, sorry, is a guy with a scanning system, so a laser scanner that actually has been pointed over the actual component, and then it takes creates a CAD drawing of it. So this is what you've got in the blue photo there at the top of that component. So it's actually a distance block. So that really creates a CAD model of what that component looks like. Every shape, every nook and cranny. And if you look on the bottom in the middle, you've got some little areas where somebody looks like they've hammered the actual component at some point. And it's even got those indentations actually modeled as part of the CAD profile. So that's how powerful these lasers, systems and CAD drawing generates the actual mirror image of what it sees. So as part of 3D printing, we can then look at optimizing that component. So what I mean by that is we've got a big solid block of cast iron there, potentially in terms of what we use currently. But is it over-engineered? Is it a case where we can reduce the amount of material we're using, therefore we can reduce the cost, but obviously try and maintain the actual performance requirements for that component? So you use some SolidWorks as a company we've used to actually go through this process with. So Solid Solutions is the overall company, sorry, SolidWorks is the software. And what we have with some of their software, they have what's called an optimizing suite of software, and that looks at the component you have currently from the CAD drawing. That's actually our CAD profile that's created with the blue image in the top there. And then we put in parameters within that software to actually say, okay, there's certain areas of this particular component you can't change. So the fishing surfaces, if you like, of this component need to be maintained because that's the shape we require. There's certain forces that the actual component's got to withstand, whatever that might well be. And we put all that information into the software system, and it comes out with some sort of wacky solutions. So there's two images on the bottom and what it's created in terms of saying, okay, for the parameters we actually entered into the software, the performance requirements that you've actually asked for, this could be something that would actually give you that still, even though it looks like a skeleton compared to what we've got with that cast block. And then the right-hand side is something a little bit more refined in terms of what we actually have come up with from the actual optimized final design. So effectively, this distance block is potentially going to be made into this shape. out of a material, yet to be determined what that material is. But this is obviously optimizing the shape and what the component looks like. We've done it with various different components, about half a dozen at the moment. But then we're going to look at the material we can actually create them from using 3D printing or some type of additive manufacturing. So that's the sort of area where we're looking to try and see what we can actually achieve in terms of using this type of technology in future. And the thing that we can do as well with components like this is if we need to actually just carry on doing the casting method that we use currently for making these components, we can actually still do that. But clearly, if we've lost the mold, but we still have the component, we can reverse engineer that to actually allow us to take a scan of that component and then use the actual mirror image, if you like, of the component you've scanned to create the shape that actually a cast mold needs to be made to allow that to be recreated as a cast iron component. So we can reverse engineer that to actually allow us to have that flexibility to be able to still make those components, but clearly not have the problem of finding out where the heck the mold's got to over the last 30 years. So it's an option for us for legacy systems, particularly where we know we don't have a manufacturer making these systems anymore and these components, to allow us to actually still recreate them. So quite a powerful way of taking things forward for us, especially with the number of legacy type of components we've got in plain and track and in SNC. So the handheld scanner, which is what I talked about earlier, this is obviously the image in the center there is looking at how we can actually scan a switch to actually using this device. It's got a laser in it to allow us to actually then superimpose a P8 wheel profile. P8 wheel profile being the most common type we have on our vehicles that run on the infrastructure. And looking from a switch derailment hazard point of view, is what this point of contact is, where these three lines actually occur. So you've got, in terms of what we actually check, which side, 55, 60 or 65 degrees of those line positions. And clearly that the contact point between that wheel and the switch rail, which is what this cross section is showing, is a key area for us to assess whether we have a derailment hazard or not. So this is what this actual device is actually being developed for. This is a very early prototype that's in there at the moment. It's going to be something that's probably a little bit bigger than a large mobile phone when it comes to it. It'll have an app on it to actually allow you to actually look at your mobile phone actually and see the data coming off that, rather than having a screen on the system, because that would mean that the actual system would be quite bulky to allow that to be displayed. So effectively, this is something that's been developed to actually show a quick and easy way of actually assessing a switch. If you are inspecting the switch and you think that something looks a bit suspect as to whether it's a derailment issue or not, you can check this with this particular device to find out what the answer is. And obviously it takes out the human factor issues of actually putting the actual gauge on the track, offering the P8 profile up to the switch rail, and understanding, well, from a visual point of view, where is that contact point? And obviously it's quite heavily influenced by human factors at the moment in terms of how we inspect switches this way. So this is something that's hopefully on the device that will actually give us that similarity, if you like, that's consistent without actually having any issues that we're taking forward from human factors that I mentioned. The other side of this, there's another particular project which is spun out of this particular device, is looking at something that's going to be able to scan the switch rail, but use all the actual gauges that we use currently for our switch inspections and do a check with those, things like an R4 sideway gauge, your switch radius gauge, gauge 1, gauge 2. So it's going to be a slightly different version of this system, but we've sort of developed that slightly outside of this particular piece of work, but basically it's spun out of this particular device being developed. So it's going to be quite interesting to see how this actually finishes off in terms of its size and its capability in the next 12 months. So we've got about another 12 months to actually work on this particular project. But again, quite a lot of influence in terms of using lasers to actually do some assessments of the instruments of the switches we look at. And then our 56V crossing, quickly moving on to that one. A lot of work's been going in to actually model what the actual wheels need to actually change in terms of the profile of the crossing itself. So that the University of Huddersfield have done this work, have been looking at around about 100 different wheel profiles of different types, different wear rates, different potential issues, which might be some that are very obscure, but others that obviously are quite common in terms of wear that we see on the different types of wheels that run on our infrastructure on the vehicles that go over that. And from that, it's been a bit of a compromise to actually understand what that profile then results in terms of optimizing the requirements for that crossing itself. So it's been a trade-off because of various different issues, such as different direction of traffic, different wheel sets, different vehicles reacting differently with suspensions, etc. So a multi-body simulation has been done with a model that's actually been developed to allow us to actually put all these potential parameters in there to actually come out with a profile that is a compromise, but actually gives us a lot more flexibility in terms of its the height of the crossing nose to wing rail relationship. So at the moment, we're looking to take this further forward to actually look at how we can manufacture this. And this is sort of areas where they've looked at how we can decrease the nose height. So the spike there on the top graph, the contact force, the blue spike is where you've actually got the crossing nose. You can see if you draw a line down to the virtually draw a line down to the bottom graph, it's got the actual cross section of the crossing. You can see as to where the actual wheel force are indicated in and what's actually happening as the wheels traverse from the wing rounds to the crossing nose. So that's been done looking at various different wheel types. So at the bottom here, you can see the P8, the different forms, the P10 and the P5 in this case. So it's just highlighting the amount of different wheels that have been considered in this and what's actually being put through the model to actually show how that actual profile would change and what sort of forces we're seeing. And this is clearly some other modelling which is looking at how stresses are applied to the gauge corner, how it moves over in terms of its trajectory as it moves from the wing round to the nose of the crossing, depending on the profile of the crossing itself you've got. So quite a lot of work's been done in terms of the type of profiles we see on crossings now and what we need to actually achieve in terms of changing what that profile looks like to reduce the forces using this type of modelling system. And finally, looking at switch rail coating. So this is something we're trying to actually look at whether there's any potential for us to coat the switch rail or maybe clad it if it's a thicker layer to reduce the actual wear rates of the switch rail. So if it's 260 grade steel, we could add a tungsten carbide type material perhaps or something like that, and whether that actually will reduce the actual wear rates of crossing at the switch trolley, give us more life and reduce the actual defects we see. So lots of work been going on to look at that with the University of Sheffield. On the bottom, we've got a scan of a switch rail that had a coating on it, and the blue area is where we're seeing the higher contact forces. So it looks like as you see where the blue is sporadic in its intervals as to where it actually hits the crossing, the switch rail. It's sort of hunting a little bit as it goes through this particular switch rail, and that's the one on the top left-hand side there, in terms of what this scan is from. And yesterday we're out at another junction just doing a scan of another switch rail just to get some profiles rather than actually looking at one that's got a coating on it. But this is the device, if you look in the center there. Again, similar to what we use for the 3D printing and additive manufacturing work to actually scan a device, our component. This is used to actually just scan the switch rail and then gives you results on the computer, which the chap on the right-hand side in the other picture is holding the computer for the operator to actually show what actual scan is creating as it goes through. And those white boards you can see with lots of dots on them, they are just markers to actually get the scanner to actually be able to pinpoint where it is in relation to the switch rail. So it's just an aid, if you like, for the scanning process. So that's work that's going through at the moment to look at creating some potential for us to actually create some test pieces to actually put on a test rig, which has got a wheel and rail interface to actually allow us to develop some more understanding of how these coatings will actually wear or not before we get to the point where we may be able to put one in track somewhere. It wouldn't go in mainline track because clearly there's quite a lot of issues in terms of safety case, etc., to allow us to get that put through. But we'll be looking to perhaps look at another railway that's environment, maybe at somewhere like British Steel's actual site where it's actually using rails to move things around the actual steelworks, but it's not going to be safety critical in terms of passenger traffic, etc. So quite a lot of work going on in that area to look at what type of coating might be useful and whether it's actually viable in terms of the potential benefits it might give us. Okay, yeah, the next stage was looking at RFID tags. So you're thinking, well, what on earth do we need to know where our SNC is? Well, The problem we've got at the moment is there's lots of legacy systems like Jogis, for example, that have been brought forward into the S&C ellipse conditioning monitoring module. And that means the legacy systems themselves, when you look at them, they've got different areas in terms of where they see or where they've been programmed to say where S&C starts and where the S&C finishes. And there lies a problem in terms of sometimes we get black holes only a few meters, maybe 20, 30 meters or whatever, where the track recording vehicle says the S&C is here, and actually physically it's slightly somewhere else in terms of what the trace is seeing. So if we can actually look at putting an RFID tag on 2 points, which we know shouldn't move, and that's the crossing nose and the switch toes, we can then actually articulate where the S&C starts and where the finish is. So when you're looking at your trace from a track recording vehicle, you can actually see where actually the issues and defects, if you like, that are actually there. Are they actually in the S&C, or are they on the approach or beyond the S&C? And this is sort of area where we can actually align all the actual systems we have to say this is now a definitive way of actually identifying where your S&C actually is, how that relates to what we've got from a track recording vehicle. The other side to the RFID tag side of things, we can actually use the RFID tag to link to other databases. So it might be a case where if we want to order a new half step or order a new crossing, we don't necessarily need to understand, has it got a radius in that leg on the crossing, or is there what sort of curve has stock rail got, and what radius do I need to put on the actual order form? This could link to something like their 1/50 drawing of the S&C, which means that information is readily available to basically be extracted from that drawing and then basically plonked into the actual order that I need to actually place. So there's no requirement for somebody to have lots of expertise and skill in terms of measuring S&C and understand where they need to actually assess whether there's any radius or any other special features in the S&C that they need to put on the order, which is clearly going to be quite an advantage for us in future. So this is just a quick run through of the actual testing that they're doing. So University of Birmingham have got this test facility in Derby, which is about 200 meters long. So they've been, whether we use a passive RFID tag, which is one that is something that can be basically, it's not actually allowing any information going anywhere, it's not being charged or anything like that, so it will only activate once the train goes over it. Or semi-passive, in other words, one that's sort of semi-alive, if you like, or awake, again, or get linked to the train as it goes over, but it's not just actually not working whatsoever as part of the actual RFID system itself. So there's areas they've been assessing, and what we've got on the right hand side is this little model train that can fire the model itself down that track around about 30 miles an hour. So it's reflecting in scale terms how a high-speed train would actually be able to read, or if it could read, the RFID tag at that type of speed. So there's lots of work that they've been doing at the university to actually understand what's possible with these tags, and clearly how we could decide which is the most optimum type of tag to use for actually taking this project forward. And again, In2Track2 itself is moving this to the next level in terms of technical readiness levels. And lastly, I think the kinematic system, which I mentioned, Repoint, we've looked at how we can take Repoint forward. And now what this system looks like, on the next slide, is a little bit more indicative of how the system might actually work in terms of its functionality for somebody who doesn't have any familiarity with it, the actual Repoint concept. Basically, this particular slide shows that it's got three bearers, three driving bearers to move the actual rails, a full head section of rail from one position to another. So it does away with the common legacy type of switch we have, where you've got that very thin blade that basically develops into a full head section of rail at the heel end. And it just moves the full head section of rail from one position to another using these drives. And each of these have got the power to actually move the actual system if any failures occurred in the other two drives. So one drive could actually still operate the machine, even in a degraded mode, but it still could mean that the actual switch could be thrown if the other two had failed, allowing that obviously redundancy to be part of the actual system to allow us to keep things moving while we can get out there and repair the other two failed bearers. So effectively, this is very similar to what we saw in the smaller photograph in the previous slide, but effectively you have two full head sections of rail. These three top bearers are the ones that are close together. They're the drive mechanisms, and they move from one position in an elliptical move, so it moves up and down in a more of an oval sort of motion, rather than sliding like we currently do with our switches we use now. And that will then obviously marry up with the other switch, the other rail end there, and looking at the potential joint design itself on the left hand side at the bottom. There's obviously a lot of work going on at the moment to understand what that joint needs to withstand in terms of its forces and the type of design that means it needs to have. So quite a lot of work going on for getting this across the board in terms of its design, and the potential then is seeing whether we can actually put a demonstrator together, whether it's a scale model or whether it's full scale, to actually put this line side. It wouldn't go in track at this stage because of lots of safety issues that we need to actually resolve, just to show its functionality and how it can actually be used in future. And clearly, if we're only using full head section rail to divert trains from one track to another, we basically get rid of lots of 053 issues that we currently have for derailment hazards. Doesn't mean to say we haven't got a derailment hazard necessarily in here, but it's going to act more like a train going around a curve rather than actually using a switch rail to use that to divert the wheels to the actual opposite track. And that's quickly a whiz through of where we've got with In2Track2. And clearly, as I said, there's lots of work going on at the moment with In2Track3 project to take a lot of these concepts further forward to get them to a higher TRL stage. So thanks for your attention.
Thank you very much. I've got a few questions in the chat function. Has anybody got any that they'd like to ask? I'll start with the ones in the chat function then and let people collect the thoughts. So tons to think about there, Phil. The first question came from Kieran Golden, who's asked, with the autonomous ultrasonic rail inspection vehicle, what would be the operational maximum speed?
Got me now. I don't know the operational speed in terms of its travelling, or if it's operation. I don't know. Obviously, it'd be quite slow in terms of being able to actually achieve that system to actually be autonomous. I don't know the speed, to be honest, that they're developing it to, but clearly with the actual trains we use at the moment, they're quite high, reasonably high speed. So theoretically, depends on the actual vehicle itself and what its capabilities are, but that's sort of higher speed, I suppose, is what we're trying to achieve in terms of its efficiency to be able to do the similar sort of inspections to what the U2 train does, but autonomously.
Thank you. There's a question from Mark Smith, who said, how would you stress it? I'm not sure exactly which bit he's referring to, but it did come in right at the very end.
Right. Need a little more detail on that. Okay.
Mark, are you willing to shout up and add some more detail? The only other comment in the chat is more of a comment than anything, is from Robbie Hardwell, and he said that Rfid tags are read at 100 kilometers per hour in Switzerland, or read at 100 kilometers per hour in Switzerland. Sorry.
Yeah, well, we're looking at that type of speed, but obviously because the LMC is at 125 in certain S&C locations, then obviously that's the area where we're trying to see is that feasible or not, to actually show how we can do that by not dismissing certain S&C because the speed's too high.
Anyone got any more questions for Phil? All is quiet.
Yeah.
It's probably then time to wrap up, Phil, and let you and everyone else get back to the day. And just want to say a huge thank you for taking the time out to do this, and for stepping in for Melanie as well. I realise you had to cover her aspects, but a huge project you're involved in, and yeah, lots of things to be thinking about, and hopefully lots of new technology to come. Yeah, a lot of them are not too far away in In2Track2 of getting to that stage, so I think it's a case of watch your space a little bit. Yeah, brilliant. I look forward to hopefully seeing some on my track soon. Thank you, and thank you everyone for joining us.